Okay, in this video I'm going to show you the latest feature of ExcSim, the reservoir simulator add-in for Excel. And the latest feature is to make a cross-section. You may know that ExcSim is a two-dimensional layer model with a 35 by 35 grid in the standard edition and 10 by 10 in the personal edition. In this case, the input is pretty much the same as in the layer mode. If you want a cross section, you just change basically one thing, but you need to understand what ExcSim does internally, because internally things happen, and it's important for you when you make your model to understand the steps. Now, what we see here is just a simple sketch of a single layer model. It's a small, this is a 5 by 5, I think. And you always have to input the top map, the top structure, and the thickness of each grid block. That's how it works in the standard layer model, and you should be used to that. Now, when you switch on the cross-sectional model or mode, what ExcSim does is it will modify the grid in two steps. Firstly, it will ignore parts of the top map. It will shift all the rows except for the first row, which will be the top row in your cross-section. It'll shift them down according to the thickness of each layer. So you'll end up with something like that. That's the first step in that ExcSim does internally. So you see that whatever top depths you gave to these grid blocks here is irrelevant. ExcSim will simply ignore them, and it will take each layer and just drop them relative to the layer above it according to the thickness of that layer. And the second step is to slide them in horizontally underneath each other so that they line up and form a stack of layers. And in doing so, also it'll adjust the width of each of the deeper layers so that they line up exactly with the width of the top layer. So the delta X values that you specify for the deeper layers, ExcSim ignores that and applies the top delta Y, and the tops of each layer is simply is calculated by starting with the top layer and just adding thicknesses vertically. So you start out entering data for a layer model and you end up with something like this. So whenever you put a well, say, in this grid block, it ends up, if that's the third block in the Y direction, that will be in the third layer of your cross-section. And of course you can put wells in all of these, say the top 4 layers or cells here, and that will be a vertical well with 4 perforations, and each perforation will be treated as a separate well. Okay, so let's look at what it looks like in ExcSim. Again, if you go to the grid tab sheet here at the bottom, click the grid sheet. This is where you define the top map input data. But in the upper left-hand corner, you see there's a orientation of the grid. The default is layer, but if you select cross-section, then you have switched mode to simulating a cross-section rather than a single layer. And if you now look at what it looks like in 3D, it looks like a cross-section, where, as we said, only the top row of the top map is relevant, and of course all the thickness. Each layer has a thickness. You can vary the thickness from one end of the layer to the other. The individual cells still have their own individual layer thickness, but the vast majority of the top map is irrelevant, as is the delta y dimension, the y dimension of the grid blocks from the second row and down, because all of these will be assigned the delta y of the top layer. So, and in this case, I've defined 11 wells, or 11 perforations of an oil producer in one edge, one side of the, let's see over here, that black one here is defined in the top 11 layers from 1, 2, 3, 4, 5 down to 11, and there's a water injector defined at the lower 9 layers in the cross section. And in this case, I've given them a minimum bottom hole pressure. I've initialized the model and taken the grid pressure, the initial pressure in each of these 11 grid blocks, and I've reduced them, the flowing bottom hole pressure, to a minimum of 100 less than the initial pressure. And the injectors are given a maximum bottom hole pressure of 100 psi higher than the initial pressure. So although there are some target rates here for the individual pressures, they are primarily determined by the bottom hole pressures. And when you run this, you'll see, let me zoom in a bit. You can see how the cone develops. You can see over here on by the producer, which is perforated in the top 11 layers. You can see how the water layer, or water, cones up into that well. You may want to look at the pressures. You can see where the drawdown is. This is the first time step, and where the injection is. The injection is down here in the last 9 layers. The production is in the top 11, and as time goes, the pressure spreads out, and as do the saturations, or the cone. The water displaces the oil. It's interesting to see, though. I'm going to keep that one open, and I'm going to open another model that I ran just a few minutes ago, in which if you scroll down to the Y transmissibility multipliers, which in a cross section, by the way, would be the Z direction, the vertical transmissibility. The default value was 1. If you change it to 0.01, we can have a look at how it differs from the case where you had a cone that developed underneath the perforations. Here you can see that water shoots up through the high permeability streaks. You can see that the red layers here are the high permeability, up to 428 millidarcy, and the green are down to is 5 millidarcy. If we look at the saturations again, you can see how the water shoots up the layers, and you don't get the same kind of coning from below. It's more a cusping coming sideways. So of course these kind of studies will give a lot of valuable insight into the understanding and help you history match production, and you can do uncertainty analysis and what ifs, and I hope you find it very useful. So I'm gonna say thank you for watching, and I'll see you again pretty soon, I hope.